Thank you, Angelica. I think it's my turn now, so I will be pretty quick because we have to rush a little bit. The scientists that precede me set the scene about the Arctic, about polar regions. So I want to tell you that there is plenty of room in the back in terms of climate science. And what I'm telling you is about a couple of projects, a couple of ideas, plus one, I would say, that we are launching for the next 15 years. So there is a lot of work to do for you that are young. I'm looking at especially on the back of the room. And that's the reason why I say that there is a lot of room in the back. As already I told, I mean, the polar region are affecting our system, but themselves are affected by anthropogenic activities all around the world, especially because of pollution that is accumulating, because of global warming that, as we have seen, is melting ice quite quickly from the top and from the bottom. But ice is not just frozen water. I mean, ice contains a lot of information inside as accumulate year by year, year by year. It accumulates information about the past composition of the atmosphere, about the gas content into the ice, and especially we know that we have accumulation in the certain sites in Antarctica, for instance. We can go back in time, as we have seen this morning, about 800,000 of years. In Greenland, we can go back in time a full climate cycles, 120,000 years, giving a lot of information. So we are seeking for very nice place where this information is maintained. And ice cores are really specific climate records because we have on the same time both forcing factor and climatic effects. So you can measure greenhouse gases which are stored inside the bubble into the ice. And looking at the ice itself, we can look at the temperature that we had into the past. So they are a sort of paleothermometers. We have to be very careful, however, because the age of the ice, and we can date the ice, is not exactly the same of the bubble because air can diffuse along the ice, but we have method to reconstruct this. For extracting information, we go on sites, possibly on a central site in Antarctica or Greenland, and we collect ice cores with some cylinders, more or less of 10 centimeter in diameter. They can be as long as 3.5 kilometers. Of course, we cut in section for the transport and so on. So we have several information from polar region and from the third pole. As Connie said this morning, third pole are extremely important because they give us also information at the regional level about pollution or what is happening really on the side. And so I promised you that I want to give you a sight into the future. So what's going on into the future of polar ice core research, and plus one things that I want to tell you at the back. So we are facing new ideas and new projects for the future. One is called Beyond EPICA, and the other one that Angelica already mentioned a little bit is ISCRIP. Beyond EPICA, what that means, EPICA? EPICA is an iconic program of the European Commission that was financed up to 10 years ago. And EPICA means European Ice Coring in Antarctica. Europe has is a leader in ice core science, and we still demonstrate in these days. And the answer of this project, and is more or less a 15-year project from now into the future, which brings together 12 nations around Europe, including some other colleagues overseas, in which European Commission, and I'm glad to have here Andrea Tilke, is investing a lot right now for the searching of the site, and in the future for the deep drilling and the analysis. And we have to go back into the past because in our future there is a lot of our past. So we want to know better how the climate system worked into the past to project into the future, and especially the sensitivity of our climate to greenhouse gases concentration into the atmosphere. That's the first goal. We will be back in a minute. And the second one, I mean, we already have seen how fragile is Greenland ice sheet for the warming, the current warming, and certainly what is the stability of the Greenland ice sheet in a changing climate. So we have two targeted sites somewhere in Antarctica. It's not easy to find very old ice. We want to go back, as I told you, EPICA project went down to 800,000 years. That's not enough because we are really in the middle of a transition on the climate that worked in a certain way before that and is working in a different way after that. It's called the mid-Pleistocene transition. Basically, what changes the frequency and the amplitude of the oscillation in between glacial and interglacial times. You want to go back even farther, so to find ice as old as 1.5 million years, which is not easy. And the second, it is somewhere in Antarctica. We are trying to sort it out. And the second thing is because in the northeast Greenland, ice stream is moving faster, as we have seen. It's moving much faster than all the model can predict. And the reason for that is that it's melting from the top, it's melting from below. Going back to Antarctica first, I want to show you a few results from this side, the EPICA side, European project for ice coring in Antarctica in a place which is called Dome C. We will mention many times these. And this is the iconic figure about the climate. This is 800,000 years ago. This is today. You see this cyclicity with the warm and cold period, and mirrored by greenhouse gases like CO2 or methane. This is, of course, before the industrial era, so we are stopping well before, for instance, the 400 part per million in CO2. But you see, I mean, the climate was warmer, as we already have heard about, more or less 120,000 years ago. Then it went back to a glacial area and so on and so forth. But as you see, I mean, the amplitude here is very high and the frequency is lower than it is here. So lower amplitude and higher frequency. So the frequency is changing because we are moving from 41,000 kilo-year periodicity to 100 kilo-year periodicity. There is an explanation behind it. There is a paper in Nature, an article in Nature a month ago, very interesting, putting in the right perspective changes in insolation and the changing of the size of the ice sheet. And we are very much interested to look what happened before that. But we need ice as old as 1.5 million years. So the question mark is exactly here. We know from marine sediments, for instance, that things change over the past and the increased frequency and the decreased amplitude. But we want to have an archive where we have both the forcing factor and the response to the climate. So we want to have the greenhouse gases, we want to have the dust, and we want to register the temperature. So we have to find a place. It's not easy. I mean, there are several possible places where we can find old ice like that. And the reason for this is that if we want to put the current changes in the right perspective, I mean, to see how much the temperature will increase because of the forcing of the greenhouse gases, we need to improve our understanding of the climate sensitivity, because it's not linear, as we have seen. I mean, there are feedbacks effect that might alter our interpretation. And if we want to instruct the models for the future projection, we need to better narrow these error bars. So that's the reason why we have to go far back into time. So we have several possibilities. I mean, Antarctica is certainly the place where we can find this ice, but there are many places. I mean, along this ice divide, which goes in East Antarctica, just to give you an idea of the dimension, to cross from this point to this point, you have to walk for 5,000 kilometers. So imagine in the most remote and pristine environment in the world, how it means to make a survey all around these places. But among the most important and the most promising places is really near Dome C, the place where we already have the record of the 800,000 years. So thanks to a coordination and support action of the European Commission, we started this adventure a few months ago. So we are already in the field. This is the first radar survey near Dome C, the place we are scientists, we have not too much fantasy. I mean, we call Little Dome C, you know. So far, that's the name. Is about 40 kilometers from Concordia station, from where we had the first big drilling. This grid that you see is the radar echo sounding profile, so radar penetrating, looking at the elevation, at least, but it's not just that. And this is Massimo Frezzotti and Rob Mulvaney in the field. The landscape is pretty boring, as you see. It's a big desert with very low accumulation. They travel for more than 2,000 kilometers with a piston bully and with all the caravan to arrive to this place, which is, it looks like that today with this caravan for Austin people and so on. This is some radar penetrating radar. We are not seeking to very thick ice, because if you have very thick ice, it means that you have melting on the bottom, and melting means disturbances in the record. We want to have a continuous record. So we are seeking for strata which are pretty horizontal. Again, the scale is a few thousand meters. It's not complete. I mean, there are other 1,000 meters on top. The scale is about 60 kilometers on this dimension and a couple of kilometers on this. So this is Little Dome C, one of the most promising places, and I will be back in a minute to that. Again, this is the bedrock elevation. We are on the top of the mountain range, but it's the place where we have the best stratification. Is quite horizontal layers. We have no melting, and all our age model give us the idea that we are at the right place. So you see basically all the layers, ice and snow layers, are quite well oriented, and is more or less to penetrate 2.5 kilometers. Just to remind you that with the Epica Dome C we drilled down to 3.3 kilometers, so it was much deeper, but less back. We could go not too far back in time. And this is what is really promising. This is again the same map. The light blue means that we are at the sea level. The red means that we are above 500 meters. This is a bedrock elevation, and the dot that you see, I mean, represent the age of the ice. Yellow means 1 million. Red and orange means more than 1 million. This is a model that we have developed in the last few months to see where we can spot best the 1.5 million years, which is more or less in the region that I've shown you. It's not just radar. Radar can tell you a lot of things, I mean, but it's not enough. We want to be sure before starting. We can't miss the point of 20 kilometers or 50 kilometers. Is big science. I mean, we need a lot of logistics, so we must to be sure to go on the right place. So we started with rapid assess isotopic drilling. So it's a fast way to go down very quickly to see the isotopic signal and see where you are in time. This was a test done last February, I mean, so a month ago, just to give you the idea of the condition in which the people worked. It was about from -30 to -60 degrees, I mean, pretty harsh condition in the field. So this is the future. I mean, we, as a nation, the European Union is investing a lot for the future, and for the next 15 years, we are willing to work on this, so there is plenty of room for that, I mean, and exciting science will come out of that. So just moving on the other side of the continent, going north, I mean, this is a zoom in between 10,000 and 60,000 years ago. This is Antarctica, this is Greenland, is in the north part of Greenland. This is what we call the bipolar seesaw, I mean, because the changes that you see in Greenland are also visible, less pronounced also in Antarctica. Every rapid warming in Greenland, which are called Dansgaard-Oeschger events, has a counterpart in Antarctica as well. Antarctica otherwise warm when Greenland is cooling, you know, so is not, those changes are not in phase. But it gives us the possibility to synchronize the ice core, and this is extremely important, and brings me to again to Greenland and to the fast-moving ice that we have, especially in the northeast part, as Angelica said. This is more or less a velocity of the ice stream, and especially this part, which is draining, as we have heard, about 8–10% of the whole glacier, is moving much faster than we can project with we could project years ago with the modeling. So we are very much interested to both physical investigation, and also, I mean, this part is also recording a lot of information. So I skipped this one because we heard about that. The point is that again, we are very much interested to this because we knew since 30 years ago that glaciers were melting, of course, pretty quickly, and they are contributing quite a lot to the sea level rise. But recently, I would say in the last 15 years, we noticed that both Greenland and Antarctica are contributing very, very much to these things. So the interest for northeast Greenland is twofold. I mean, because it gives us a lot of information. It might give us a lot of information about the future evolution of the whole Greenland ice sheet. And again, on this side, we might have a very good record, climatic information over the last 80,000 years, and we are very much interested on that. But then there is something else that I want to tell you. We heard that the poles are not just the North and the South Pole. We have a third pole, and all the glaciers belonging to high elevation mountains ranges like the Alps, like the Himalaya, like the Tibetan Plateau, the Andes, are under threat. They are melting very, very quickly. We are losing a lot of ice because of that. And ice is not just frozen water, as I told you, although in some part of the world, and for instance in La Paz in Bolivia, the water supply coming from glaciers is about 30%. So when we will lose the glaciers over there, it will be a lot of problem from a social point of view. And in Himalaya, it would be even worse, I mean, because there are about 900 million people relying on the supply of water coming from the glaciers. So ice is not just frozen water, as I told you. It keeps a lot of information, and we have the duty to safeguard this information for the future before they will completely disappear. So again, we have seen many glaciers this morning. This is much closer to where we live. This is in Marmolada, is in the Dolomite. You see this hole is a hut in the rock, dug at the end of the 17th century, 890 something. To enter on this hut, you have to go down of a few steps from the ice. Sometime at the beginning of summer, you couldn't enter on that at the beginning of last century because there was too much ice. This is today, I mean, 60 meters of ice is gone completely, I mean, in the Dolomite. And this is one of the glaciers which will soon disappear. There is a model done in the French Alps that says that by the end of the century, all the glacier below 3,600 meters will be completely gone. And again, with the ice, we will lose information. And if I have to think what we do today and what we have done in the last 20 days and the progress we had in ice core science, looking at very tiny molecule, organic molecule, inorganic stuff, or proxies for biomass burning and so on, and if I have to project them into the future, what we will be able to do in 50 years from now, a complete chemical imaging and chemical tomography looking at DNA storing to the ice, but in 50 years from now, this ice will be gone. So we have a duty, and the duty we have is to save this ice for the future generation of scientists. So we launched this project, which is called Ice Memory. The official launch will be on the Wednesday, the day after tomorrow, in Paris at UNESCO headquarters in Paris, because we want to give a very international dimension to this. There is a fully international project. I just want to show you a small part because we are living in Italy, which is a lot of alpine glaciers around. So we have our own target, our Chinese colleague, US colleague, South American colleagues, and Russian colleagues. They have their own targets. So we want to go there to collect ice core, to quickly study to see what is inside, and then after that we have done that, we want, for instance, to move from Colonifeti to Venice, and then from Venice we bring them to Christchurch with a research vessel, stored and frozen, of course, and then to Mario Zucchelli Station, which is our Italian national station, and then again to Dom C, which is this site where we have an average temperature of minus 52 degrees, and we want to create there a repository for the future generation of scientists. So first step would be to go for the sampling. Sampling is not very easy. I mean, sometimes you have to climb up to high elevation mountain to go back with yak or other carrying the sample in your shoulders. So it's not very easy, but after that we plan to roughly analyze the ice in chemical lab, all in our laboratory. We want to give a very rough and fast analysis. You see, this is a melting device that we use to analyze the ice. This is just half a meter of a section of half a meters. You can get hundreds of data looking at seasonal changes, dating, or whatever. And then the next step would be to transport down to the station and then inland with the traverse, as we have seen before. So we want to create this sanctuary, a long-term storage for the future generation of scientists in this side, to go with the traverse from Dumont d'Urville, which is the French station here, or to go from Mario Zucchelli, which is here, and to drive your piston bully up to here, it takes about 15 days, good 15 days, and it costs a lot, of course, but it's something we have to do. And this is the cave that is already existing. You see on the bed, on the background here, you see the station we have there is a joint Italian-French station that is permanently run all year round. And this is the cave already set up for the moment. We have to excavate a new one for the ice core, for the long storage. And this is the DOMSI. And as I told you, it's a truly international program. I mean, ice is like a library. I mean, we want to try to save really a lot of information for the future generation of scientists, and it's clearly an international program. So basically, we have 2+1 target, and these targets are dealing with Greenland. We, on the next 5 to 10 years, ISCRI project will go on. Angelica will be in the field in July. I will be in June. I will be in June. So everybody is going to work on there. We are looking at the stability of the Greenland ice sheet, of the northeast Greenland ice sheet. We look at the climate record. Certainly, we can cover all the Holocene, the last 10,000 years, plus the transition at a very, very high resolution. And then Antarctica, we had to look at the transition from the 40 to 100 kiloyear war. This is the mid-Pleistocene transition is a very peculiar period of time, and the sensitivity of our planet to greenhouse changes can be looked at into these archives. And then the very last things that I told you, we want to create this third project as a repository for the future. Not too much science. That's the reason why we had problem in supporting this project. I mean, because when we go to founding agency, they say, that's not really science. And that's true. I mean, we just do a little of science just to characterize the site, but then we need to store it. It's a more or less an heritage study that we want to see. And we are really feel it as a legacy for the future of generation of scientists. So if you want to adopt a glacier, just come to me and I will tell you how to do that. Thank you very much. Now I changed my hat. I put the hat of the chair of the morning session. We have now an aperitif outside offered by the organization, and the Cipriani is organizing that. We will reconvene at 2:30 sharp, okay? 2:30 sharp for the afternoon session. Let me thank all the speakers of this morning. It was really inspiring for me as well. You know, I'm working in this since many years, but you always see something new. Thank you very much, and thanks to the young scientists in the back.